Hi students, in last class we're discussing about dry corrosion. So let us do wet corrosion in this lecture. We are going to discuss about the principles of electrochemical corrosion or wet corrosion. So the learning outcome would be at the end of this lecture you'll be able to understand the principles of electrochemical corrosion. So what is wet corrosion? So wet corrosion, by name itself, it says there will be presence of moisture and otherwise known as electrochemical corrosion. So this will form like an electrochemical cell where we require an anode, cathode and an electrolyte. And this will happen at two conditions which are when two dissimilar metals or alloys are in contact with each other in the presence of an aqueous solution or moisture. Secondly, when a metal is exposed to a varying concentration of oxygen or an electrolyte. And in the first case, when a metal is exposed to varying concentration of oxygen or an electrolyte, we have so many examples which we'll be discussing later. Okay, let us first of all see what exact mechanism happens in electrochemical corrosion. There could be two things that can occur, depends upon the medium, what medium the metal is in contact with, whether it is in contact with acidic medium or neutral or alkaline medium. Say a metal is in contact with an acidic medium, the first type will be evolution of hydrogen. Okay, this is a metal made of maybe iron. Here what happens until they're uniform corrosion or dry corrosion only will occur. But if there is any non-uniformity like this, okay, it will undergo electrochemical corrosion. What will happen is like two different areas are generated, anodic area and cathodic area, and when they come in contact with moisture or an medium, it will undergo corrosion. Okay, so the anodic area will behave like this, where loss of electrons, say if this is iron, iron loses electrons to produce Fe2 plus. Oxidation takes place at anode. And at cathode, since we have acidic medium, there will be H plus ions which will gain electrons to produce hydrogen. So this comes under hydrogen evolution type corrosion. And in the case of alkaline or neutral medium, absorption of oxygen will take place. When an ion is in contact with neutral or electrolyte in the presence of oxygen. Okay, and here also what happens is the metal will lose electrons at anode. Fe loses electrons to produce Fe2 plus, and at cathode the oxygen will gain electrons to produce OH minus. Okay, now what happens is the Fe2 plus and OH minus combines to form iron hydroxide, and it depends upon the amount of the oxygen that is present. If the amount of the oxygen is limited, there will be formation of iron 2 hydroxide, and if oxygen is in excess, it can form iron 3 hydroxide. So everything is a rust. Okay, iron 2 hydroxide is a rust and iron 3 hydroxide is also rust, but it depends upon whether it is going to be yellow rust or brown rust or black rust. In the absence of oxygen, there will be formation of hematite or black rust. So, electrochemical or wet corrosion, there must be an anode, cathode, and there must be an electrical potential difference between the electrode. There must be a metallic path electrically connected with both electrodes, and there must be an electrically conducting medium. Okay, like it need not be a complete kind of electrodes. Okay, where there is non-uniformity, the metal itself will behave like anode. Certain parts will behave like anode, and certain parts will behave like a cathode. And these are the differences between chemical corrosion and electrochemical corrosion. So obviously the chemical corrosion takes place in dry condition and takes place in wet condition, and this is a direct one, and electrochemical corrosion takes place through the formation of a cell type corrosion, and it can take place in heterogeneous or homogeneous metal surface. It can take place only on heterogeneous metal surface. And chemical corrosion, we call it as uniform corrosion. This is non-uniform corrosion. And corrosion products accumulates at the spot, and corrosion products accumulates at the cathode. And one example for electrochemical corrosion is differential aeration cell. Aeration, that is air, difference in concentration of air or oxygen. Okay, see here, the we have iron immersed in sodium chloride solution where we have excess oxygen, and the same iron immersed in sodium chloride oxygen, but it is in the nitrogen atmosphere, so the oxygen concentration will be less. Okay, so there is a difference in the concentration of oxygen which will lead to differential aeration. This will take place in pitting, crevice corrosion, etc. So same electrode material, same electrolyte, temperature will differ or oxygen concentration will differ. So corrosion inside heat exchangers or boilers will undergo such kind of corrosion. So based on the appearance of corrosion damage, we have uniform corrosion, pitting corrosion, crevice corrosion, galvanic corrosion, intergranular corrosion, stress corrosion, cracking. I've listed only few here, but we have so many types of corrosion. And electrochemical corrosion, I'll just give two examples because we listed two conditions when two dissimilar metals are in contact with an electrolyte or a conducting medium, that is galvanic corrosion. When a same metal is exposed to varying concentration of oxygen, that is differential aeration. Let us see some examples. So galvanic corrosion, when two different metals are in contact with an electrolyte, the more active metal will behave like anode and the less active metal will behave like a cathode. If you're comparing zinc and iron, zinc is more active, so this will be anodic. Iron is less active, so it will be cathodic. Obviously, zinc will undergo corrosion. If you are comparing iron and copper, iron is more active, copper is less active. So iron will undergo corrosion, copper will be safe. And such kind of corrosion we call it as galvanic corrosion. Zinc and iron couple, copper and iron couple, steel screws in a brass marine hardware. So steel screws will be anodic. So steel screws will undergo corrosion where brass will be safe. That's why whenever we make nuts and bolts, they should be made of the same metals so that corrosion can be prevented. This is an example for differential aeration. You see a zinc rod immersed in sodium chloride solution partially. Okay, so the zinc rod inside an electrolyte will be exposed to less oxygen, and the zinc rod above the sodium chloride solution is exposed to more oxygen. Here, less oxygenated area will behave like anode, and more oxygenated area will behave like cathode. So at anode, always oxidation takes place. So loss of electron, zinc will lose electrons to produce zinc 2 plus. On the other hand, at the cathode, there will be absorption of oxygen because sodium chloride is a neutral solution. So absorption of oxygen type will take place. Oxygen accepts 2 electrons and there is production of OH minus. Now zinc and OH minus will combine to form zinc hydroxide. So slowly zinc is getting corroded and it will dissolve in the electrolyte. Some examples for differential aeration is pitting corrosion, crevice corrosion, pipeline corrosion, corrosion on wire fence. See, this is If at all you place a water droplet on any metallic surface, below the water droplet it will be less aerated and all the other surfaces will be exposed to more oxygen. So this will behave like anode and all the other parts will behave like cathode. So this is enough to generate differential aeration, and this is known as pitting corrosion. So continuous corrosion will take place at anode. It will start like a small pit and it will end with a very big cavity. Anode. Iron will lose electrons to produce Fe2 plus and at cathode absorption of oxygen. Now iron 2 plus and hydroxide will combine to form iron hydroxide. If there is excess oxygen, there will be formation of iron 3 hydroxide. Crevice corrosion. Whenever you join any two different metals with the help of crevice, the parts below this crevice will behave like anode and all the other parts will behave like cathode. Pipeline corrosion, same pipe, but they're exposed to different types of soil. One could be clay soil, another could be sandy soil. Sandy soil is more aerated compared to clay soil, so more aerated area will behave like cathode and less aerated area will behave like anode. So this part will undergo corrosion. This is pipeline corrosion. And wire fence at the joints, they are less aerated area will behave like anode and all the other parts will behave like cathode. So this is the area where corrosion will start. So corrosion rate expression, we can express in millimeter penetration per year or grams per square meter per day, and inches penetration per year, miles penetration per year, like that. Okay, so corrosion rate, if it is less than 0.005 IPY, good corrosion resistance. If 0.005, the corrosion rate is between 0.005 and 0.05, it is satisfactory. And if the corrosion rate is greater than 0.05, it is unsatisfactory. So in last lecture and this lecture, we were discussing about types of corrosion like chemical corrosion, electrochemical corrosion, and under electrochemical corrosion, we also discussed about differential aeration and galvanic corrosion. So as an engineer, you must be responsible in choosing the metal as well as analyzing what are the different types of corrosion and how to solve it. So the learning outcome, I guess it is achieved. The students are able to understand the principles of chemical and electrochemical corrosion. Thank you.